e, yep, e to the 0.002 t, and this would be what? In millions. Nice, I like that.
I don't think that's how you spell it.
Do we have an L value here?
Yes.
What is our L value? 5,000. It tells us our K, gives us our K value, right?
Yeah.
1.78. Wow, that's fast. Okay. So what do we have here? P of t is equal to 5,000 over 1 plus a e to the negative 1.78 t, like this.
Yep.
What's left? What do we have to find?
A.
What was a? Do you remember what a is equal to? L what? L minus P naught over what? P naught. So do we know what our L is?
Oh, 5,000 minus 10.
5,000 minus 10 over what? 10. So what is it going to be? 499? So we end up with P of t equals 5,000 over 1 plus 499 e to the negative 1.78 t.
Yeah, I got it now because I didn't know how.
You got that? Is that good now? Cool.
That's good now.
Cool. Decrease. Use your graph to estimate the length of time until the rate at which the people are becoming infected starts to decrease. So where is the fastest rate of infection happening? The halfway between, right? Halfway between. So you know that wherever you start right here, L over 2 equals y equals L over 2 is going to be the time when when it's growing the fastest. That's the inflection point. So whatever path you choose, whatever solution curve you draw, where's the steepest positive one going to be? At y equals L over 2, correct?
Oh, wait, so that's always the case with everything.
Yes, all logistic.
Okay.
Yes.
So you get like 2,500, and then you just.
Well, so yeah, it's y equals, so it's going to be y equals 2,500, correct? Right. So it says, okay, so we have a solution. So what do you set that equal to?
Okay.
You take this and you set it equal to 2,500.
Okay.
Now, you're going to need your calculator to do that probably, unless you are really sadomasochistic. You solve this right here, right? You solve that.
Yeah.
Make sense?
Okay.
Now, the thing is, when you take the derivative of the top, you put it over the derivative of the bottom, and you're suddenly done. It's real simple. What's the issue with this one? Can anybody realize what the issue with this one's going to be? What's the issue with this one?
Yeah, let's do that.
Okay, I like the specificity of your answer, Kevin. So, pieces of this are kind of annoying to deal with. What else? What gets annoying?
X to the x is e to the x ln x.
Yeah, so you can do it that way, but the point is, this is more involved because just because you're taking the derivative doesn't necessarily mean it's going to be nicer.
Easier, yeah.
Just because you take the derivative doesn't mean it's going to be nicer all the time. In this case, when you do the derivative, it doesn't come out to be that bad. It just comes out to be annoying, okay? It just comes out to be annoying. It becomes out annoying. There's a lot of x's in here. There's a lot of x's. And I love questions that go, negative 2. Like, that's pretty cool. So I just want to throw out there that just because you realize you can use L'Hopital's rule doesn't mean you're going to have just a cakewalk to the end. Can you embed L'Hopital's rule inside L'Hopital's rule? Like, can you end up with an indeterminate form after you've taken the derivative and put it over the derivative? Yes, you absolutely can. So when you do this derivative, as Kevin pointed out, what do they start with? Oh, you have to do d dx of x to the x. Oh, look, there it is. It's a pain in the butt. It's a pain in the butt. But it allows us to actually find a numeric answer to this thing. It allows us to find a numeric answer. So I put the algebra in here so you don't have to do it. I just want it to be there as an example of, just because it's L'Hopital's rule doesn't mean it's going to automatically be simpler after differentiation. You can rewrite it in one step. And what does this become when you rewrite it? It becomes, yeah, limit as x goes to infinity of x over e to the x. And as x goes to infinity, this is infinity over infinity, so is it L'Hopital's rule? Yes. You apply L'Hopital's rule. That was the h with over and equal signs. H, I'll make it a little bigger. So you end up with, it's going to be the limit as x goes to infinity of 1 over e to the x. So what is it going to be? 0. Yeah, it's nice. This was a nice one. So it was obfuscated a little bit. Could the obfuscation be a little deeper? Yeah, it can be a little deeper. So here's a few of them where the obfuscation can be a little deeper. Let's look at A, for example. A. Let's look at A. Is there a quotient? Can you get the door, Pinky? Is there a quotient? Well, there's not a quotient in that one. Could we force a quotient? How could we force the quotient, Tanmay? Yeah, so you could do x to 0 from the right of ln x over what?
1 over x.
1 over x. Is that an indeterminate form? As you go to 0 from the right. Why does it have to be from the right?
Because if you go,
You can't go from the left for which function?
ln.
ln, right. It's not, there's no, ln is not defined for 0 left. Exactly. So can we apply L'Hopital's rule here? Absolutely. And you have the limit as x goes to 0 from the right. What's the derivative of ln?
1 over x.
1 over x, and then what's the derivative? This is x to the negative 1. What's the derivative there?
Negative x to the negative 2.
Negative 2. So what do we do with that? Maybe simplify it a little bit. What is that? It's going to be the limit as x, 0 from the right, of 1 over x times what?
Negative x cubed. Or no, negative x squared, sorry.
Over 1, right?
Yeah, so we just get
Negative ln x to the 0 from the right of what?
negative x.
So what is it going to be?
Negative, just not.
No, negative is just 0.
Isn't it going? It's going to 0 in this case, right? Are we okay with that? Did I do the math right? Did I do the math right? Like this is going to be negative x and 1 over like this. Did I do that right? Am I okay? You guys are my checkers here. Good. Okay. Do on the right. What's that natural log allow us to do? What does this now allow us to do right here?
You take the 1x down.
You can take it. Thank you. So we have ln y is equal to the natural log, the limit. I got to really be clearer with this. The limit as x goes to infinity of 1 over x ln x. Is that correct? Yay. So you have natural log of y is equal to the limit as x goes to infinity of ln x over x. Hey, is that indeterminate? Yes. Can anybody tell me just in their head what this ends up coming out to right here? What's the limit as x goes to infinity of that? Can you do it in your head?
0.
You sure?
No. 1.
You sure? Is it 0 or 1? Who thinks it's 1?
7.
I'm not asking for explanations here. Sometimes I don't. I just want, who thinks it's 1? Who thinks it's 0? It is 0. Here's why. You take L'Hopital's rule. When you do L'Hopital's rule on this thing, you end up with the limit as x goes to infinity of 1 over x over 1. So what's that going to be? 0. So what do we now know? The natural log of y is equal to 0. Are we done? Is our answer 0? No. We want to know what y is. What is y in this case? Yes. Y is 1. Nice. So it gets obfuscated in different ways. One of them is you need a log to undo the obfuscation. Now, I already referenced this one above. I already referenced this one. This one right here, x to the x. It's quite fun. What do we need to do in order to solve this one? Anything different? Yeah.
So x
here. And you're doing the whole limit of this, by the here, parentheses like that. What do you think you have to do to set this one up? What do you think you have to do? Yeah.
Change it to secant.
That's a good idea, actually. Don't do that, but that's a good idea. It doesn't get you anywhere.
Oh.
I'm just helping you out here. That's a great idea, though. What else can you do with two fractions that are subtracted from one another? Subtract them. Don't forget, like, you can do the basic math operations that you know how to do, right? So what is this going to be? It ends up with the limit as x goes to 0 of what? Sine x minus x over x sine x. In what form is that? Let's see. Sine of 0 is?
0.
So the top is definitely 0. Oh, and 0 times sine of 0. Oh, is 0. So is this indeterminate now?
Yeah.
Yeah. So now can you do this thing? Yes, you can. You apply L'Hopital's rule and see what happens here. We have the limit as x goes to 0 of what? Cosine x minus 1 all over what? Cosine x, derivative of something plus, what is it? I did the derivative of both. I did it wrong. You can't do that. You can't do that, Mr. Seamon. Don't let me do that.
1 sine x times x cosine.
Times what?
X cosine.
Yes.
Cosine x like this?
Yeah.
And can you plug in 0 into this thing? What's cosine of 0?
1.
So we have 1 minus 1 over.
Over 0 plus.
0.
Then it doesn't work.
0 plus what?
0.
Okay, so is it indeterminate again?
Yeah.
So we're going to stop here and pause here, but theoretically, what do we have again? Another 0 over 0, right? You do it again. You do it again and see if it cleans up. So here's the thing. Sometimes it works, sometimes it doesn't, but you are on a path here at least. You are on a path. You are on a path. 1, 2, 3. You come forward 1, you go to the right 2, and you go up 3. 1, 2, 3. You locate that point. Are we going to be doing very many of these things by hand? No. We are not going to graph in 3 dimensions by hand that much at all. But you need to know how to read this. You need to know how to read this. So for example, that point is 0, 0, negative 1. You don't go anywhere on the x-axis. You don't go anywhere on the y-axis. And you just go down 1 point. You just go down 1 point. You just go down 1 point. What is this a visual representation of?
The rectangle
Yeah, it's a rectangular prism. It allows us to find the distance between 2 points.
Oh, alright.
It allows us to find the distance between 2 points. It allows us to find the distance in between 2 points. So, anybody want to guess how you find the distance between 2 points in 3 space? What theorem do you use? Izzy. It's just a 3-dimensional Pythagorean theorem. When you move into 3 space, basically 2 things happen. Either all of the formulas and theorems just add on exactly what you think, or they become wildly different. It's really cool when new things get invented, when you get to 3 space or new things get created, but in this case, this is an example of when things stay exactly the same. So if it was just in 2 dimensions, like if you wanted this distance right here, you do this length and this length squared, add them together, and take the square root. So what do you think? What do you think it is in 3 dimensions? Same thing. It's the exact same thing. Exact same thing. So it's going to be x minus a squared plus y minus b squared plus z minus c squared square rooted. It's just a logical extension. The cool stuff happens when we create new things that don't exist in 2 dimensions.